Hello, welcome to Electronics Education. I'm Vincent Chang. Today we are going to continue our lesson on the subject of MOSFET. MOSFET channel length modulation effect explained. So channel length modulation effect is one of the most important what I call second order effect happen in a MOSFET. So second order effect describes something that's beyond the ideal situation. So first of all, this effect happens when the transistor is operated in saturation mode. Saturation mode. So think about this. So what's the definition of saturation mode? What's the constraint? First of all, the channel is present. Channel has been induced. The VGS has to be greater than the threshold voltage. The second constraint, this is the first constraint. And the second one is it's beyond pinch-off point. So VDS, drain to source voltage, has to surpass the overdrive. The VDS is larger than the overdrive, the VGS minus VT. Then you will see this. This is what happens, what we see when the transistor is operated in the saturation region. In other words, the source end, in the source end is non-pinch off, but at drain end is pinch off. L is the distance between the source end and the drain end. So it's called physical channel length. Physical channel length is determined by the manufacturer. All right? And this shape is kind of a taper shape. On the source left-hand side is narrower, but on the right-hand side is broader. And then goes gradually wider and wider. This is filled with the depletion region. It's the depletion layer. And then this length is the depletion layer width along in the horizontal direction. All right? So you can also measure the depletion layer width in the vertical direction. All right? So I'm talking about the delta L is measured along this direction, the horizontal direction. In other words, that's the distance between the blue point, the pinch-off point, and the drain end. All right, it's the depletion layer width denoted by delta L. And then L minus delta L equals what? The L effective. The L effective is the region where the electrons are abundant. Still abundant, non-depleted, undepleted. So it's called effective. The conduction will be effective. Channel length is called L effective. Effective channel length. Here comes the channel length modulation, the central point of this lecture. All right? So in the saturation region, if we keep pushing the VDS, what will happen? Then when VDS increase, right, you increase, look at the slide, you increase the drain voltage. So it's the N plus P, I didn't say the P, but you know the substrate is the P substrate, all right? So N plus P junction, when you increase the drain voltage, then what? Then you increase anode cathode. Cathode, right? You increase the cathode end voltage. So it actually increase the reverse bias of the drain to body junction. Let me repeat that. When you increase VDS, you increase the reverse bias of the N plus drain to P substrate, drain to body junction. So based on the semiconductor, based on the PN junction theory, the junction theory, on the subject of semiconductor physics, When you increase the junction reverse bias voltage, then what? Then the depletion layer will be widened. Okay? So depletion layer will be widened. But it's the widened in a two-dimensional. It's a little bit complicated. So it's widened in this direction. Also, it's going to be widened in this direction, 45 degrees. And also, it's going to be widened in horizontal direction. Anyway, when we increase the VDS, then what? Then delta IL will increase, which means pay attention to the pinch-off point. Then the pinch-off point will move toward which end? This end, right? Will move to this end. And also, let me go back. And also, I said that the depletion layer also will be increasing along the vertical direction, right? So it's going to be widened this way, and also this way, right? And then what? Then delta L is increased, which means the L effective will be decreased, right? The L effective will be decreased, but pay attention. If you have ever learned, if you now have to go back to the previous lecture on the semiconductor, on the MOSFET basics. So the pinch-off point, the voltage is fixed. At pinch-off point, the voltage at pinch-off point equals what? Equals the overdrive. Let me repeat that. The voltage at the blue point, the pinch-off point, equals, you can write this down, VGS minus VT. So actually it's fixed. It's always fixed. So which means on the left-hand side is 0 to a fixed voltage. In our previous example, in the MOS physical operation lecture, I used the example of 4 volt, okay? So let me assume it's 4 volt here. So you increase 4 volt, you change 4 volt, but within a shorter distance. What does that mean? What does that mean? Means the electric field will what? Will goes up. The electric field within the effective channel will goes up. So when the effective electric field, within the effective channel goes up, then what? Then what? It's the mechanism of a carrier drift. It's the drift. So the electron will be more accelerated, right? So because the field goes this way, and then electron is going to go this way. So which means the electron drift velocity. The drift velocity will goes up. So when the drift, I will take out my video. Okay, let me finish this. Finish this. So electron velocity goes up, then what? Then what? The ID will goes up. Here's the result. So this is the physical illustration for channel length modulation. I encourage you to pause and take note. Make sure you understand all the detail. But in summary, if someone asks you, what is the channel length modulation? You don't have to go such a detail like what I just did. But you have to highlight the 3 part, right? When VDS increase, the symbol behind my video is the ID goes up, right? I just show you. So you highlight 3 points. When VDS goes up, and then the effective channel length will be shortened. And then ID will increase. In what region? In saturation region. Let me repeat that. What is the channel length modulation? What is the channel length modulation? What region? Saturation region. So when MOSFET operates in the saturation region, and then if we keep increasing the VDS, if VDS goes up, then the effective channel length will goes down, will be shortened. And then the ID will keep going up. ID will keep going on. This is the physical explanation, illustration for the MOSFET's channel length modulation. Very important. Channel length modulation. And then in saturation region. But before this, in the previous lecture, I didn't talk about this, right? I said beyond the pinch off point is the constant current source. When you keep increasing the VDS, ID will remain constant. And ID will be independent of VDS, which is not true in a practical situation. If the channel length modulation effect is considered. So this is the practical current voltage characteristic when channel length modulation has been considered. So you will see this. It's not constant current source. We'll keep going up. 3 volt, same. 4 volt, the same. And 5 volt, the same. Now think about this. If you work in a factory, the semiconductor manufacturer, you are the device engineer, and you design every detail for the MOSFET, and someone came along, or your boss asked you, or your colleague asks you, how's your channel length modulation? How's your channel length modulation? Is it severe or is it's not severe? So how you describe? But that's the adjective, right? So we got to describe the degree of this effect in a more quantitative way instead of a qualitative description. So how strong, how severe this effect is, then we do this. You see a family of curve, right? A group of curve. So then we extrapolate back to a negative axis. When VDS goes up, L effective goes down and ID goes up. I have done this, you know this. And then, here it is. We use the extrapolation. We extrapolate the family of the IV curve back to the negative axis. And the intersecting point is defined as the VA, or 1 over lambda. The dimension for VA is volt. And for lambda, is the inverse of volt. And VA is positive. Lambda is positive. So the degree of this channel length modulation effect is described by a factor or a voltage. So it's called channel length modulation parameter, lambda. So lambda is called channel length modulation parameter. So see this equation? This equation, before that, we didn't have the second term, right? I didn't show you the second term. So in reality, when the CLM, the channel length modulation, is considered, then it's described when VDS going up in saturation region again. In saturation region, when VDS goes up, ID goes up. But think about this. If lambda is small, which means what? Which means the device doesn't exhibit a very strong or conspicuous the channel length modulation effect. So if lambda is small, then VDS increase a little bit or increase more, and then ID increase a little bit. But when lambda is large, that means the effect is stronger. So lambda is called channel length modulation parameter. And this is the equation that you should be very familiar with when In what region? Saturation region. And when the channel length modulation effect is considered, right? Takeaway. So first take away this equation in saturation region when channel length modulation effect is considered. And what happened? And what happened? You got to explain what happened, right? When VDS goes up, effective channel length goes down. ID goes up. So we have now come to the end of the lecture. In the next lecture video, I'm going to show you, teach you about another important second order effect, which is called body effect. Very interesting. Look forward to the next lesson. Thanks for watching.